Welcome to this explainer. Today, we're taking a dense, highly technical engineering standard and flipping it into a clear, step-by-step visual guide on exactly how we measure the behavior of melting plastics. If you've ever wondered how the plastics in your car, your phone, or your medical devices are manufactured with such incredible consistency all over the globe, the secret actually lies in a document known as ASTM D1238. Let's break down how this crucial standard works.
All right, here's our roadmap for today. We'll start with the melt flow problem, look at the extrusion plastometer's anatomy, cover Procedure A for manual measurement and Procedure B for automatic timing. Then we'll hit some advanced tests and variations before wrapping up with precision, prep, and pitfalls.
Section 1. The melt flow problem. To really get why this standard even exists, we've got to ground ourselves in a true industrial nightmare: inconsistent plastic melting.
Imagine a factory floor trying to mold a million identical parts, but every single batch of raw plastic flows at a slightly different speed when heated. Total chaos, right? So that brings us to our core metric, melt flow rate, or MFR. We are fundamentally tracking how fast melted plastic flows under specific conditions. Measured in grams of material extruded every 10 minutes, it's essentially the universal language of polymer consistency for global manufacturing.
Now, what is absolutely fascinating here is this direct quote from Section 5.3. We're measuring a behavior. It's an empirical indicator of uniformity, not some absolute fundamental trait of the plastic itself. If you change the testing environment, the plastic's behavior changes entirely. We're not finding a fixed number, like an atomic weight. We're testing how a specific batch acts under very specific, highly controlled stress.
Moving on to Section 2, meet the extrusion plastometer. Before we test anything, we need to know the anatomy of the gear we're using. Essentially, this machine is a giant, hyper-calibrated, heated syringe, often called a melt indexer. A weighted piston pushes molten resin down through a thermostatically controlled heated steel cylinder and out through a tiny die at the very bottom. Seems simple enough. Apply weight, melt the plastic, push it out. But the real genius here isn't the mechanics, it's the tolerances.
And those tolerances are staggering. We're talking about margins of error smaller than a human hair, just to ensure consistent friction and heat transfer. The cylinder bore? Exactly 9.5504 millimeters. The surface finish has to be a mirror-like 12 RMS to keep the plastic from catching or dragging. If these dimensions are off by even a tiny fraction, your friction changes, the heat transfer shifts, and boom, your data is entirely useless.
Section 3. Procedure A. Manual measurement. This is the hands-on approach.
This is typically used for flow rates between 0.15 and 50 grams per 10 minutes, where an operator is physically cutting and weighing the extruded plastic. The whole sequence requires exact timing, especially that strict 7-minute preheat to soften the material without causing thermal degradation. Heated too long, and the plastic chemically degrades. Too short, it won't flow. The operator actually has to wait until the piston is exactly 46 millimeters above the die, make an initial cut to ditch the preheat material, start a timer, and then make a final, perfectly clean cut to collect the test sample.
So, how does this translate into the testing math? Well, the faster your plastic flows, the more sample you need, and the shorter your time intervals become. Otherwise, you'd end up with a complete molten mess on your lab bench. For really fast-flowing plastics, you might only collect it for a few seconds. You weigh that tiny sample, then multiply it by a standardized factor to figure out what the flow rate would be over a full 10-minute period.
Section 4. Procedure B, automatic timing. This is the automated upgrade.
Procedure B runs our testing range all the way up to 1,500 grams per 10 minutes, because let's face it, when plastics flow that fast, human hands with a spatula just aren't quick enough. This method entirely removes the human element of manual cutting and weighing. Instead, it relies on sensors to track exactly how fast a specific volume of plastic is displaced, and then it mathematically converts that volume into a mass measurement using the polymer's known melt density.
And 6.35? That number represents the exact millimeters of piston travel the automatic timer measures for materials flowing under 10 grams per 10 minutes. We're talking about measuring time to within 1/100th of a second. The system tracks the exact moment the piston drops that 6.35 millimeters. For faster materials, it might track a 25.4 millimeter drop instead. It's all about capturing a hyper-reliable window of data without any operator interference.
Section 5. Advanced tests and variations. So, what happens when plastics behave drastically differently? ASTM D1238 has built-in adaptations for edge cases, like extreme high-speed flows over 75 grams per 10 minutes. That's where procedure C steps in with a half die, literally half the height and half the diameter of the standard die to slow things down. The standard bore is about 2.1 millimeters wide. The half die shrinks that opening to just 1.048 millimeters while keeping the exact same length to diameter ratio. This creates the extra resistance needed to get accurate readings on incredibly slippery, fast-melting polyolefins.
Then we have procedure D, which is just brilliant. It calculates a flow rate ratio, letting engineers see how a single batch of polymer reacts to shifting pressures in real time. Rather than using just one weight, an automated system adds or removes weights during the test. You divide the flow rate at the heavy weight by the flow rate at the lighter weight, and you get a single dimensionless number. That number gives manufacturers massive insight into the molecular structure of that plastic.
Section 6. Precision, Prep, and Pitfalls. To wrap up this explainer, we have to talk about the rigid rules keeping all this together.
Because honestly, a dirty machine guarantees useless data. We're fighting a constant battle against subtractive loads, where even a microscopic layer of burnt plastic creates friction against the piston. You can't just casually wipe it down. Sometimes they deploy pyrolytic decomposition, literally baking the die in a 550 degrees Celsius furnace with a nitrogen purge just to turn residual plastic into ash. And you have to be careful, because even the slightest scratch from a cleaning brush can alter the bore dimensions and completely ruin your accuracy.
And don't think automated drive systems are immune to error either. They require rigorous calibration against master load cells that mimic the combined weight of the piston, ensuring applied forces stay within a razor-thin 0.5% tolerance. Everything, the temperature sensors, the timers, the weights, must strictly trace back to national standards like NIST. You are constantly proving the machine is doing exactly what it claims to be doing.
If a fraction of a millimeter or a single trapped air bubble can completely derail industrial uniformity, it leaves you wondering just how delicate the balance of global manufacturing truly is, doesn't it? We rely on plastics to be utterly predictable, but as the standard shows us, that predictability is only won through obsessive, relentless precision. The next time you hold a perfectly molded piece of plastic, you'll know exactly the kind of microscopic scrutiny it took to bring it to life. Thanks for joining me on this explainer, and keep questioning the science around you.